All right. Thanks, Ron. And thanks to all of you for inviting me back to do another talk. I also want to thank you very much for accommodating the fact that I'm not actually able to be there in person. Family commitments right now are making it so that I'm spending a lot of time up here in Santa Barbara. So I appreciate that you be able to work with me on this here. The talk I want to do this evening is kind of a follow-up, actually, to a talk I gave about 7, 8 years ago now for you folks. Back then, I was talking about what was a cool new discovery, the very first interstellar object. And so things have been moving along. We're now up to three that we've seen now. And so I want to give you that. And so I'm calling this one Atlas and the Hyperbolics. And that's what I want to talk about here today. So here's what I want to do. I'm going to start out with a little introduction to orbits. I'm not going to get too far into it, but I want to mainly give you a sense of where does this word hyperbolic come from, and what does it have to do with what we're actually talking about here. Um, then a little bit of history of the interstellar objects, and I'll remind you a little bit about the previous two that have come through the solar system. Then we'll get on to the star of today's show, which is 3I Atlas, a newly discovered object that's coming into our solar system. And I'm going to tell you a little bit about it. I'm also going to do some comparison between Atlas and the other two, so we can talk about what it's like, how these objects compare. Um, and then in the second half of the talk, I want to start moving into something we can begin to do. We can really begin to think about. And that is the whole question of, so what can we say about interstellar objects in general? And specifically about these ones. What are the things besides what we're seeing directly? What can we go back in time and try to get a little bit of their history here? So that's what the last part of the second half of the talk will be about. Then a little bit of conclusions of sort of where I see us right now in the study of these interesting objects. So let's dive in and look at orbits here. And really, the question I want to focus on here is when we see an object in our solar system, how do we tell that it actually comes from outside of the solar system? And this is something that, fortunately, we can go right back to the very roots of orbital mechanics, back to sort of 17th, 18th century stuff here. Um, when folks sort of applying Newton's laws of motion to orbits, starting with Newton, but then going beyond that, realize that if you look at what we call the two-body problem, which is really just one body with massive and has lots of gravity, and then a second body that's small enough we don't care how much mass it has. Um, and we look at how those behave, and you apply the mathematics of the to the physics involved. It turns out there are three what we call analytic solutions. And that means things where you can make a pretty solid description of how something moves, how something behaves, without having to plug it all into a computer and run it through step by step by step. But you could just describe it as a simple function, simple mathematical function. And this little picture illustrates what this is. And if you've done much geometry, you will have seen these specific types of curves. They are very familiar curves in the world of geometry. One of them is what's called an ellipse. An ellipse is a closed shape. It looks sort of circular or oval shaped, and um, we describe an ellipse. One of the key numbers we use to name it is something called the eccentricity. And eccentricity is really a measure of how stretched out is it. So an eccentricity of 0 equals 0 is simply a circle. And that's the gray shape here. And so a circular orbit is an eccentricity zero orbit. It's sort of an extreme example of an ellipse. And in that case here, in these curves we're showing, the little f is the focus of, it's the mathematically it's described as the focus, but you can think of it as that's where we put the sun. So this is the shape of an orbit going around the sun. Yeah, as I say, equals zero is a circle. Actual real orbits around the sun are never quite exactly zero. They're always a little bit oval shaped. And the more oval shaped they are, the more eccentric they are. You see that as a slightly out of round shape like this E equals zero point 0.5. Those are all from a both from a mathematical point of view and from an astronomer's point of view, they're all pretty similar because they're all really just closed orbits. They just keep, and the object just keeps coming back along the same path over and over and over again. And it's a good first approximation of how planets move around the sun, how spacecraft orbit around the Earth, how the moon orbits around the Earth. It's a really good, useful place to start. Um, you know, just as an aside, if you really want to do it right, of course, you have to remember that they're the universe is not made of just two masses. There's all these other things pulling on it, on everything that's orbiting. And so real orbits are a little bit more complicated than this, but this is a good starting point. Okay, often when we talk about things in orbit, that's as far as we get. We talk about closed orbits and we say, yep, okay, orbits are ellipses, planets orbit in ellipses. That's one of Kepler's laws. And we say, great, we've got this down. But really, the same equations give you two other kinds of answers. And so one of those is what we call the parabolic solution. That's eccentricity equals exactly one. So you can imagine, if you take that ellipse, that oval shape, and you get it more and more and more stretched out. Oh, that was interesting. I didn't know that was going to do that effect. Um, you can get this long, skinny orbit, and but those are still all closed orbits. But if you push something up to high enough speeds, when it goes around the sun, it'll go out and it won't ever come back. And the thing that's right on the limit, the orbit that's right on the edge of that, is the parabolic orbit, E equals 1. Um, Nothing ever hits exactly equals 1, but a lot of things will come very close, as I'll talk about in just a minute. Okay, that's if you're right on the edge. If you're just barely at the moving fast enough that when you pass the sun, you'll go off into space and you won't come back. Another way to look at that, if you think of the term escape velocity, the speed you need to go to escape from an object gravitationally. Something in an elliptical orbit is moving at just a little, at somewhere less than the escape velocity. Everywhere in its orbit, it's always less than escape speed. Something that's in a parabolic orbit is always, throughout its orbit, moving at escape speed. Now, escape speed changes depending on how far you are from the sun. So when you're close, you have to be going really fast. When you're far away, you don't have to go very fast at all. The third option, mathematically, the third solution to this is what we call a hyperbolic orbit. And that's one where we say the eccentricity is greater than 1. Another way to look at that is that object, as it's going around the sun, is always going faster than the escape speed everywhere in its orbit. Um, Now, that's the blue curve that you're seeing here. And yeah, if you're not a mathematician, the blue curve and the green curve don't look that different. They are map and qualitatively, the result is pretty similar. The most important difference is that in the green curve, as it gets further away from the sun, it keeps getting slower and slower and slower because it's going right at escape speed. And when it's way, way out there, long past the planets, its speed is tiny, 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 but it never quite goes to zero, but it's getting very close. For the blue curve, for the hyperbolic orbit, it's not only moving faster than escape speed, but it's going fast enough that even if you went all the way to infinity, it's still got a velocity. It's still moving, and it could be moving pretty fast even. So the hyperbolic orbits are the ones that are way faster than just what you than substantially faster than what it would take to escape from the sun. Okay, those are the three solutions, the three options. Up until 2017, when we looked around at all the objects moving around in our solar system, at least all the natural objects, we threw a few things out that were faster than this. But everything that we measured, I was either elliptical. There were some, and these were all comets that had velocities that had orbits that were either right at or just beyond the parabolic. So either parabolic or just barely hyperbolic orbits. The largest eccentricity we knew of before 2017 of any natural object in the solar system was 1.057 or something like that. So it was just barely not quite held on. We were pretty sure that those were still objects that, at least until recently, had been part of our solar system. In fact, they were comets. They had started way out in the Oort cloud, and I'll come back and talk more about the Oort cloud in a little bit, but the big reservoir that's far from the sun. And they came in, and as they were coming through the planetary system, they got too close to one of the planets, generally Jupiter. And Jupiter changed its orbit. Jupiter's gravity gave it that extra little tug that resulted in it then moving fast beyond the escape speed. And so when it went past the sun, went out, it's not coming back. It had shifted from a closed ellipse, even if it was a long, skinny ellipse rather, to an open shape to a hyperbola, and off it was going. And until 2017, that's it. We had never seen an object that had clearly come from outside of our solar system that was coming into our system. 2017 is when that story changed. And the reason that changed, most important reason really, is technological. In the early 21st century, in the first quarter of the century now, we've really started shifting how we look at the sky. We can now do large scale digital sky surveys, and we have several of these that have been developed now that have the specific purpose of looking for stuff that's moving through our solar system. And there's lots of reasons for that. One of the major ones is honestly because we want to, if something's going to come and hit the Earth, we want to have as much warning as we possibly can. So that's certainly one of the major reasons why. But this also lets us simply study what's moving around in our solar system in much greater detail. It lets us see stuff that we simply would have missed otherwise, because our observations were hit and miss, and we may or may not have seen something coming through. And so in 2017, one eye Oumuamua, I used to be better at saying this, one eye Oumuamua was observed. And this was the first object that was a true hyperbolic object. It was moving well beyond the escape velocity of the solar system. Its path did not take it near any of the planets. So there was no way that it was that it had gone through any kind of gravitational perturbation to throw it into this orbit. Um, and so it unambiguously had come from outside of our solar system. Now, there were some things that were surprising about this. Um, there was no coma, no tail observed. It was not an observed comet. As I'll talk about later on, we kind of expected that when we started seeing interstellar objects, they would be comets. This one wasn't. It was also kind of a weird shape and a few other things about it that were kind of cool. So, and I'll say some more about those in a minute or two here. But um, nonetheless, this was big news. It was very cool. We finally, for the first time, seen an object from outside the solar system passing through our solar system. Great. A couple of years later, 2I Borisov was observed, moving much faster. You see, look at the eccentricity on that. 3. Oh, right? That means it's moving. It's really whipping through the solar system. The diagram here, it shows uh, uh, both Oumuamua, and that's the red curve, and Borisov, that's the yellow one. And you notice the difference. There's two things that are two things that are happening here that make these orbits look really different from each other. Oumuamua, notice it does like a hairpin turn and around the sun, and it whips right back out again. And that happens whereas Borisov, its its orbit gets bent a little bit, but that's all, and then it just continues on its way. And there are two reasons for that. One, Borisov was moving a lot faster, and so the sun just didn't have as much effect. Also, Borisov didn't get as close to the sun. Oumuamua got in really tight. It was much less that it was just a few tenths of an AU from the sun at its closest approach. Um, so that plus the slower speed is why it's got that more of that V shape orbit rather than just a gentle curve there. Borisov, in many ways, was more like what we expected. It had a coma, it had a tail. Um, that's like okay, that's kind of what we were expecting to see. Then just over a month ago, we finally saw the third one, 3I Atlas, and it was 3I Atlas was discovered using it should be 3I, not 31 there, was discovered July 1st using the Atlas Observatory System, which is really a set of several telescopes spread around the world that are built specifically to look for objects that might possibly threaten the Earth. That is their stated intention, what they're doing here. Um, it gives you a pretty good sense of what it's like. This is the little field here, that little square in inset. That is the discovery photo. And they noticed actually it takes multiple pictures, but they noticed something moving in that incredibly dense bit of star field there. And that's how they were able to clue in that they had an object. Now they do this all the time. This is they're always finding stuff. But this one really was set apart. Um, it has, when they were able to figure out the eccentricity, uh, it has an eccentricity of 6, which just means it's really whipping. Um, it was observed July 1st. It was at 4.5 AU. It's now less than 4 AU away already. To give you a sense of just how fast this sucker's moving. 4.5 AU is almost Jupiter. That's how far out it is. And it's effectively about to come through the main asteroid belt, at least as far as distance. It's not quite in the plane of the belt there, but um, once they had the orbit of this and they realized where it was, well, other folks who were doing surveying the sky started looking at their data and say, "Hey, wait a minute, did we see this too?" And you may have seen in the news, a month or so ago, the Vera Rubin Observatory has just been going through it's basically its test runs. They're trying out their cool new cameras that surveying huge chunks of the sky, and they will be eventually looking at the whole sky over and over again with this. And so, in their test runs, it turns out they were looking in the right part of the sky, and so they got some observations of this prior to the actual discovery announcement July 1st. Theirs goes back to June 21st. Yes, which is actually looking for exoplanets. It's studying exoplanets. Also happen to be looking in the right part of the sky, and it observed this back in early May. They got some images of it at about 6.4 AU. And from the brightness of what they saw, they think that this object had a coma. It's looking like a comet. It's got a coma, but it's got a coma at 6.5 AU. It looks like, which means it was showing activity way out past on the other side of Jupiter's orbit. Um, that's unusual. It's not, we've seen that before with comets, but it suggests that there's not just water ice in this thing. It's pushing out, it's got stuff evaporating from it that is that is much more volatile. That's carbon dioxide or carbon monoxide, or we'll talk about some other options here. Okay, so let's take a look at the orbit of this of the 3I Atlas. As I say, it's an extreme hyperbolic orbit. One way to describe that is to talk about V infinity. How fast was this thing going when it was far from the sun? And this is the speed relative to the sun itself. So how fast did it come at us here? And the answer is about 58 kilometers per second. Um, the Earth moves around the sun at about 30 kilometers per second. Escape velocity from Jupiter is about 60 kilometers per second. And that's from Jupiter's cloud tops. So yeah, that's a really high speed by solar system standards. Perihelion, it will get closest to the sun in late October. At that point, it's going to be moving at about 68 kilometers per second. And yeah, that's not a big difference in speed. And that's because it's going so fast. The sun just doesn't have time to speed it up that much. So yeah, it's covering several AU per month, or substantial chunks of an AU each month here. Um, Closest approach to Earth, unfortunately, is almost 2 AU out, and that's going to be in December. And you'll see that here in the simulation that's showing how it's going to come through. Note, if you're planning on traveling, it's there's going to be a really close approach to Mars on October 3rd. So if you're heading out, and then if you really want to go out to the outer solar system, there's another close approach by Jupiter next March. So look for that. If like I say, if you're traveling here in the next few months, but the closest approach to Earth, as I say, is December. It's well past perihelion, well past when it's closest to the sun, and we're just not going to get a great view because when it's closest to the sun, the Earth is going to be on the opposite side of the sun. So unfortunately, we're not going to get a great view of this. That's that's too bad because it would have been kind of cool. Um, let's see here. This is what I want. Okay, When this was discovered, now it was discovered for over 4 AU out, 4.5 AU out, it was magnitude 18. That's still fairly bright for a comet-sized object that far away. Um, there we go. When, if you're wanting to observe it, and yes, it certainly will be observable with the kind of telescopes I know some of the members have, it's probably going to be getting in about magnitude 11, 11 and a half, 12, somewhere in that range. Now, estimating comet brightness is a dark art. Nobody really wants to admit to whoever doing it themselves. It's a little scary, and you'd never be entirely sure. But we don't really expect it to be something that's going to be easy to see, especially because in September and November, that's going to be basically just on either side of when it's going past the sun. Um, you're going to be fighting twilight basically to observe it. So, yeah, like I say, it'll be a tough one to catch. But I know we've got some good observers in the club, so best of luck. Go for it. Okay. All right. Let's see how these three interstellar objects actually compare with each other now. We have three of them, so let's take a look at them. Velocity at infinity, as I said, Atlas 58 kilometers per second, Borisov 32, Oumuamua rather 26 kilometers per second. Um, these are not wildly unexpected speeds. Okay, this is the kinds of speeds we see for the stars moving around us relative to us here in the galaxy. So, yeah, that's reasonable. Um, the sizes, very different sizes. So there's a certain amount of debate on the side of it because, uh, first of all, for Uamumu, there was no coma. You'd think, okay, great, we can see it directly, but it was roughly small. So was really so most of our so I'll say we don't have any actual the photographs we have it just looks like a point. That's why I didn't bother to put in a picture of it. I just put an artist's conception because it really gets across the key thing about this one. It looks like it was very long and skinny. It looks, and whether it was a disc shape or a sort of needle shape or what is not entirely clear. The shape is coming from how the brightness changes as it sort of tumbles around through space. So that's it clearly the brightness changed pretty dramatically. We think that means it, like I say, that's a sort of long and skinny shape. Different people have got different models of what they think actually works best for that. For the other two, the shape is hard to tell because you've got this bright coma surrounding the nucleus, the actual solid thing down at the center here. So this coma is evaporating ices of various sorts, along with dust that's being kicked off the surface, and but from sort of modeling what that how that gas and dust behaves and seeing, yes, there is a little bright point in the center. That's got to be the solid object down there somewhere. People have estimated sizes of Borisov as about half kilometer. Um, and then Atlas, uh, they typically are running a diameter of around 1 to 6 kilometers. So three rather different sized objects. And that's going to be important here in a few minutes when I start talking about what this suggests, or at least what we can do with these. Perihelion, closest distance to the sun, as I was saying, Oumuamua got really close, much closer than Mercury. Unfortunately, with Oumuamua, we did not see it before it came into the solar system. We only saw it on the way out. So we did not have any direct observations of it prior to its closest approach to the sun. One of the interesting things people have asked about it is, did that close passage by the sun actually evaporate a lot of stuff off it? That's a distinct possibility. We don't know. Like I say, we didn't see it, so that's unfortunate. Uh, Borisov, Atlas, both quite a bit further from the sun at their closest approach, so not nearly as dramatically affected by the sun itself. Composition, always a tricky thing with these because you're basing it on reflected sunlight in large part. Maybe you'll get some ions in the coma when you can see the coma, but of course the coma is only telling you about the stuff that's evaporating off the surface, and you don't know what else is on the surface. All of them look, from what we can tell of the light coming from the surfaces, they all look like either comets or really, really dark cometary type asteroids. They all have that kind, the actual nucleus itself all seems to have that basic composition. The two that actually have comas, we've seen evidence of water in both of them. There's uh, there were definitely some carbon compounds, cyanide and cool things like that in Borisov. We think there's probably stuff like carbon monoxide and carbon dioxide in Atlas simply because it's active so far from the sun at such a low temperature, so evaporating at such a low temperature. Water just shouldn't be evaporating that far away. But we don't have good spectral lines to confirm that. So that's still kind of fuzzy there. So these are have been our three interstellar visitors. They've come in from elsewhere in the universe. So what else can we say about these things? And in a sense, this is why I think it's time we can start saying some things here that go beyond just the individual objects here. First of all, just a kind of an interesting point, when you've got one of something, it's a fluke, right? Okay, yeah, we saw it. We don't know. Are these common? Are they not? Who knows? You got two, okay, maybe that's interesting. Maybe that's a coincidence. Once you get three, you got to start taking this seriously. Okay, interstellar objects are a real thing. There really are objects from the interstellar medium that come rolling through our solar system. That's kind of the first thing. We can now start saying this is a population of bodies. And we may not be able to characterize it too well yet, but we can be a little more confident that yes, they really are, these really are something that's wandering around out there that we had not until recent years been able to observe. So, can we say anything meaningful about this population? Can we say anything about where they're coming from, how old they are, things like that? So that's what I want to start looking at. And I'm going to start with the age, which might be a surprising one to think about. But it turns out there's a cool trick we can play to say something about how how long we think they've been wandering around in our galaxy. So an interstellar object is when it's moving through space, it's going to be subject to all the same forces, especially all the same gravitational forces that affect the stars that we see. So in a sense, they should be doing the same thing the stars are doing. And we know about the motion of stars. We've been studying that for a long time. And one thing that's kind of we've learned about stars and known about them for quite a while is that within our galaxy, stars mostly form, at least within the disk of the Milky Way, they're mostly forming right along the plane. So if you think of the Milky Way as this flat disk, the star formation is really concentrated right in the central plane of that disk, a nice flat middle of the disk. And they start out forming with pretty much circular orbits. And then over time, they start scattering. Yes, they feel each other's gravity. They also start feeling gravity from the larger scale structures of the galaxy itself, like the spiral arms. And that makes increases both their eccentricity, that is how out of round their orbits are, and also the inclination, which is a measure of how far vertically they go, right? They start out with effectively zero inclination. They're just staying moving around the galaxy right in one plane. And then they start running, feeling tugs from other things, and that single plane starts turning into more of an up and down as they go around the galaxy. So the effect of that is that as things get older, they start having more velocity relative to the other stuff. Because if everything's moving along in a nice flat plane, then they're not moving very fast. This star and this star are really moving at pretty much the same speed. So there's barely any velocity difference between them. But once they start having little ins and outs and ups and downs, then yeah, how fast they move relative to each other starts becoming important. They go faster and faster and faster. And so when we look at our galaxy, the younger stars are mostly what we call low velocity. They mostly have relatively low speeds relative to each other. The older stars are higher velocity. They move faster relative to each other. They make a thicker population within the disks because they move up and down a lot more than the ones that are still near the central plane. Um, and so, if that's true with stars, we expect that those should also be true with ISOs. So here's a way, and this is a preprint that came out just a few weeks ago that talked about, well, can we estimate the ages of these of the three ISOs we've seen based on how fast they're going? And they're, I'm just being kind of sort of pretty general about it here. They actually did a pretty good job of breaking the motion up into the different components, sort of towards and away from the center, and towards and away along the path, and up and down through the through the plane of the disk. And they sort of looked at how those components are likely to affect things. They decided to focus mostly on the up and down motion because that seemed like it would be the best indicator of age. And so then they came up with estimates of age. And they said for Oumuamua, which was the lowest velocity one, a little over 1 billion years. Borisov, close to the same age as the solar system, around 5 billion years, and Atlas at around 7 billion years. Now, I know that the graph here that I've shown comes straight out of the paper is a little hard to interpret. So let me kind of break it down for you here. Um, the bottom the bottom axis here is age, and that's in gigayears. That's billions of years. So the red dashed line is their estimate for the age of Oumuamua. Um, but you see there's then this kind of reddish zone around it, which gives you an idea, which looks like it's around 1 billion or so years wide, which starts to give you a sense of what the size of the error bars are. And then you've got this green curve, that's a green dashed line, that's Borisov. But again, the uncertainty in that number, it's around 5 billion, but the uncertainty means it could go all the way down here to less than like more like 2 billion, all the way up here to almost 9 billion years old. So the uncertainties on this are huge. And then again, with Atlas, the best estimate of the age coming in at about 7 billion years, but it could be 12 billion. or 11. Could be 11 billion, or maybe it's down somewhere around four, maybe three and a half. So, and I'll say for folks who are interested in the statistics of this, those are one sigma uncertainties. In other words, there's a 68% chance it's within those error regions. That's a pretty, those are big error bars on that. Um, so can you be really confident on those ages? No, not at all. But you could imagine if we started having more of these, this could start to become a much more meaningful kind of ground. I think it's probably reasonable to say Atlas is probably older than Borisov, and which is probably older than Oumuamua. Beyond that, yeah, well, we don't want to go too far with that. But what if it is 7 billion or 7 or 8 or 9 billion years old? If Atlas is that old, that velocity we're seeing puts it in with what we call the galaxy's thick disk. So this is an edge-on view of the Milky Way, and that yellow region. So you can see the little yellow dot there. That's the sun, the bulge, the the normal, really obvious part of a disk galaxy is the green part. That's the thin disk. Thick disk is somewhat less dense, um, but it also has much older stars. So these are some of the earliest stars that formed in the disk of the galaxy. And as you see, and so Atlas might belong to that. Atlas might come from a star in that population, which is kind of cool. So we'll come back to that and talk a little bit of what that might imply. Okay, here's another question we could ask about interstellar objects. How many of them are out there? So a couple of things to know. First of all, two of the three interstellar objects that have been discovered were discovered as part of these big surveys. The third one, Borisov, actually was found by an amateur. He was just looking. It's like, hey, look, there's this cool comet. Um, but the others were found as part of surveys. And so that's a thing to keep in mind. We're going to start seeing more of these just because of these surveys. All right. So we've got three different interstellar objects. Right now, our problem is they're from three different size ranges. And we really expect that the 100-meter objects, there should be probably a lot more of those than there are the half-kilometer objects, there should be a lot more of those than there are a couple kilometer objects. It's so our, we can't just combine them all and say, hey, what does this tell us about how many ISOs we're looking at? Because there really are different, they really are sampling different parts of the population. One thing, though, you can do is you can say, okay, we look at a survey like Pan-STARRS or Atlas and say, how many, what's the likelihood of it seeing one of these things if it comes through a certain volume of the solar system? And then we can use that to at least set an upper limit on how many of them there must be. And I've read a few papers that have been doing this, and they're kind of quick to say, well, we'll assume that we've seen one in the course of the lifetime of that survey, and so we'll assume that's what we get, one per 10 years or however long that survey is. That to me seems like a kind of a weak statistical argument, right? You saw one. You don't know if that's one in 10 years or one in 1,000 years, right? That's that's not a great assumption there. But again, Taylor and Sigelman again, based on the fact that Atlas discovered the Atlas survey discovered the Atlas um, interstellar object, they argue that these things are probably that there's probably a sort of average density of one of these for every 10,000 cubic astronomical units in space. which seems like a lot. And again, I think that's an upper limit. I don't think that's a meaningful. You can say that with any great confidence, but if you do that, you can actually work it backwards. It turns out this may actually put a limit on how big the Atlas uh, Atlas ISO actually is, because it is kind of tough right now to figure out how big that object is, that little point down in the center of the coma of this comet. So to understand how you do that, we first need to ask the question, where do these things come from? And the answer to that comes from our model of how the solar system forms. So when we look at our solar system right now, we know all about the planets, and more recently, we've been observing the Kuiper belt, which is this disk of small bodies that produce many of the short period comets that orbit around the sun, and Pluto's out there too. But then there's the Oort cloud. And so if we take all of that stuff we've just talked about, that's this little tiny dot down at the center. And we think that are surrounding all of this is this cloud of trillions and trillions of icy bodies. And the reason we think that is because every once in a while, one of them gets perturbed into the inner solar system, and we call that a long period comet. So back around, people have sort of worked on this for a while, but way back in 1991, Dave Hughes did a little work on on modeling this and trying to figure out. So when you when you actually uh, if you actually make an Oort cloud, well, how do you make an Oort cloud? Turns out you make an Oort cloud by planets like Uranus and Neptune and maybe even Saturn throwing other small bodies, planetesimals, out of the solar system. And it turns out that's a kind of inefficient process. In our own solar system, in fact, and I'll say part of what makes it inefficient is Jupiter. Because if you got a Jupiter would, if something gets too close to Jupiter, it's gone. It gets thrown away. Bye bye. We're not seeing you again. So Uranus and Neptune can throw things into really long orbits, and then and then maybe when they're out there they get perturbed, and so they don't come back. They just kind of stay in these very distant orbits. When you work out, well, how efficient is that process? It's really inefficient. For every one object, every one planetesimal that gets captured out in the Oort cloud, you wind up throwing something like 25 of them just out of the solar system completely. So if that's true, and if that's how it works in solar systems, that would suggest that we actually form that when solar systems form, they should be throwing planetesimals out. They should be making interstellar objects. This is a normal part of the formation process. And what Hughes didn't know in 91, but we now know, is that most stars have planets. And there's still a lot of debate about exactly how many planets and how many of different sizes, and especially when you get to the ones that are farther away from the star. But nonetheless, planet formation is a pretty normal part of how stars form now, we now realize. And if that's the case, then it should be pretty common for, as when planets form, that a bunch of small stuff, especially a bunch of small icy stuff from the outer solar system, should get thrown out into space. And so we should expect to see a whole lot of these kicking around. I should make a quick aside here. Just a few years before this paper came out, I was trying to figure out what my doctoral thesis was going to be, and so I asked my advisor. So we at this point we've never seen any interstellar object. We've never seen anything clearly from outside the solar system come through. Does that put any real limits on how many of these things are forming, on maybe how common planet formation is, because how many or how it works? And he said, well, I don't know if anybody's done that. Go ahead and do the calculation and see. And I did a back of the envelope calculation, and I came to the conclusion that, well, maybe, maybe there's kind of like a 50-50 chance that we might have seen one in the last few hundred years with an uncertainty that was several orders of magnitude. So like, okay, fine. This was not a good thesis project. I went ahead and did something else instead. But that's and Hughes, I'll say, did a much more careful, much better job than I did with it, and came to almost the same conclusion. So it's pretty. So that's prior to actually observing these things with the technology we had 40 plus years ago. Um, yeah, that's kind of where we're. That's kind of what we expected. Couple of interesting things that come out of this model, though. First of all, these things should be icy, right? These are things that come from the outer solar system, the outer part of planetary systems, which leaves us with the problem of Oumuamua, which didn't seem to have a lot of volatiles, didn't seem to have a lot of ice. And so there's a couple of different suggestions out there. Maybe it did come from that, and somehow it lost all of its ices, either before it came into the solar system or when it had that close pass by the sun. Um, or maybe it was one of those rare things that was actually formed in the inner part of a solar system and then got kicked out through interactions with with the planets along the way. Because you certainly can do that. And something formed in the in our solar system, so anything that forms in the inner solar system and then has a close pass by Jupiter has a decent shot of getting kicked out. So that's you could still get a certain amount of that, just not nearly as much as you would icy stuff. The other interesting thing is that, okay, these form. We think that these come from forming solar systems. The thick disk stars, the old stars, the ones that were some of the early stars that formed in the disk of the Milky Way, are what we call low metallicity stars. That means that, and I'm using astronomers' definition of metallicity, which means anything that isn't hydrogen and helium. So carbon, oxygen, silicon, anything like that, astronomers call those metals. We drive chemists up the wall that way. But the these things have like a quarter as much of this kind of stuff as as what the sun has. These stars do, and so we've often wondered, okay, can you make planets in around stars that have that little metal? Well, we have certainly seen a few solar systems that are like that using in exoplanet surveys. So yeah, we knew it was happening, but this is a real confirmation because these ISOs are clearly made out of more than just hydrogen and helium. They clearly are made out of heavier stuff. So they had to have formed in a in an environment, in a solar system type environment, um, and that low metallicity is still enough that you can make make planetary type bodies and clearly planetesimals with it. Okay, so then the other question we might ask about this is how many of these things does the average solar system form? And you can do that. You could say, okay, let's do the calculation. Let's divide our number density of ISOs by the number density of stars and see what we get. And again, the folks who did the study for the Atlas comet and came up with said, well, we think we're seeing a certain density of these, which suggests that, you do this division, you come up with something like 10 to the 13 interstellar objects the size of Atlas should be formed around the typical star system. Well, if that's a real number, then it puts a real limit on how big Atlas could be. Because if Atlas is too big, if Atlas is like a 10 kilometer, which is not an uncommon size for a comet, then you figure out, well, how much metal do all the stars around us have to have produced, have to have put into making ISOs in order for that to happen? It turns out you'd have to use all the metal in all those stars, which is a problem because we don't think they're that efficient. So that would suggest that one of two things: either the estimate for how many interstellar objects of that size there are is too was too big, and it's really less than we just got lucky seeing this one, or else the diameter of Atlas really is quite a bit smaller than 10 kilometers. The authors of that paper were suggesting around 2 kilometers. I've seen other more direct observations who are, like I say, that are putting it, as I say, anywhere from from kilometer up to several kilometers size range. So it's probably not a 10-kilometer comet. But that's kind of interesting. You can start to work backwards like that. Um, all of these results, all of these numbers I'm throwing out right now, are first guesses. There's sort of long lists of assumptions that have to go into them because we don't have the statistics. That could change. If we start seeing more of these things, we could start talking about, well, how many interstellar objects of different sizes does each solar system make? And can that in turn tell us something about the population of Jupiter-sized planets versus Neptune-sized planets in the far outer parts of these solar systems, which are really hard to get a hold of observationally? This might actually let us start to talk about that in a more meaningful way, and be able to tie that together with the observations we now have of exoplanets. So that's where I want to wrap this up. Okay, we have seen three unique interstellar objects. From each one, they're different sizes, some variation in composition. There's certainly very different or very different speeds, suggesting maybe different ages. But when you look at the stuff that's coming online, like the Atlas survey, like the Vera Rubin Observatory, that's going to be observing the sky in incredible detail all the time, and doing whole sky surveys constantly, we're going to see a lot more of these things. And what I'm hoping is in the next few years, we can move from this kind of what we're doing now, which honestly, it looks like butterfly collecting. Ooh, look, this is a cool one, isn't it? Oh, wow, that's a neat one too. Instead of looking at them one at a time, and start looking at them really as populations, and start being able to do real solid statistics and say, how many of them are there? What is the size distribution? What compositional variations? What is the velocity distribution? And really start to get a handle on what these like. And we're at the break. I won't say we're there yet, but we can see it coming. And I'm reminded of the mid 1990s with exoplanets. And those of you who are old guys like me or old girls like me may remember back when those first few exoplanets were observed, right? 51 Peg, and then first was one, and then there was two more, and then there was one, and you were kind of, okay, we're getting one at a time, and then it sped up, and then it sped up, and then the Kepler mission, and then they started coming in at like hundreds and thousands. And I think that's what we're going to start seeing here, is we're going to start seeing that shift from this looking at each individual one and trying to pull as much information as we can out of each one to being able to look at whole populations. And that's going to be really cool. And I think over the next, say, decade, I think that's going to happen, and we're going to be, and our understanding of ISOs is going to change tremendously. So this will may tell us things like how does solar system formation change over time? How is it what are some of the other ways that other solar systems are different from ours as well as similar? So a lot we can learn here that I think we're just about to get to. And that's what I've got for you tonight, folks.
Okay, thank you.
Ask for questions.
Yes. Any
Yes.
questions? But we only have a short time.
I got one real quick one here. I was wondering, is there any serious discussions about possibly building a spacecraft that could take close-up pictures and measurements of IO or interstellar?
ISOs. It's I've seen suggestions pop up a couple of times. The trick, and I'll say the way you would have to do that is you'd have to have something basically ready to go and then wait.
Exactly.
And then have good enough observations that you really do get to see it at 5, 6, 7, 8 out, so that you can then have a chance. The other problem with these things is that they are moving damn fast. So
Yes.
if you wanted to put something, you wanted to get something, it would probably have to be something small that you could get accelerated up to a really high speed. We're talking sort of a New Horizons type thing, but maybe with a bigger booster, to really get it up to the speeds, because it's got to be at solar system escape velocity without doing any kind of gravitational assist. It's just got to get there and uh, get into uh, line up for it. And of course, most of them are not coming in moving at the same direction the sun is. Right? They're at all kinds of different angles.
Right.
So you got it. You may have there's a good chance you have to compensate for the Earth's motion as well. So right now, I think it'd be really tough. Of course, if we start seeing them finding them much more frequently, and if we ever actually have the budget to have a spacecraft just waiting, maybe it'll be worth trying. But I think it'll be a while before that's going to be realistic.
Okay.
Any other questions?
Yeah, I've got one more here.
Great.
These objects, you analyze the gas behind them. And is it similar to the our regular comets that we see that rotate around the Earth? The gas basically the same?
To the extent that we can tell, yes. Borisov, yeah, we've gotten lots of lots of good observations on Borisov. Looked like a pretty garden variety long period comet, honestly. Atlas, we're still still in early days here, and we'll see what happens as it comes in further into the inner solar system. They have it's hard because it's hard to pick out the lines, because most of the light you're getting with this thing is really reflected sunlight reflecting off the dust. So you're not getting really strong emission lines from the gas here. And of course, you have things like our own atmosphere has all the same gases, which is a real pain. Um, so but yeah, they've certainly picked up water in both as gas, and I think even signs of liquid and or solid water in there as well. So they've got, those are about the only lines I've actually seen for for Atlas so far. Um, but I'm sure there are lots of other folks, lots of other telescopes are pointing that way right now, trying to get spectra. And so as it comes further into the inner solar system, I'm sure we'll start getting a better handle on what that coma looks like.
Any questions?
No.
Well, I'll ask it later. I'm just wondering, like, visual magnitude of these kinds of things.
Yeah, about,
So-
about 11 later, but yeah, go ahead, Dr. Kary.
Yeah. So, I mean, yeah, right now it's in the mid-teens. As I say, it was 18 at when it was first discovered. It's gotten a little brighter as it's moving in closer, but yeah, when it's we're probably not going to get better than 11 or 12. 11 and a half is the number that's getting kicked around right now. And but again, some of us are old enough to remember something called Comet Kohoutek. And that was a notorious example of a comet that looked really bright when it was out by Jupiter. And then when it got close to the sun, it was like hardly anything. So, like I say, predicting comet brightness is a bit of a dark art. I don't put great faith in it.
Okay.
Guess that'll do it, huh?
Yes, we're gonna thank you very much.
All right. Well, thanks for having me, folks. Always fun to see you folks.